Hi all. I'm going to walk through a common coding interview problem and explain how you should go about solving it, and then solve it step by step for you. Getting to the answer and coding it is important, but it's just as important, if not more so, to explain your thought process along the way and communicate what you're thinking, how you're thinking, so that your interviewer can guide you if necessary and so that they can understand how you're going about solving the problem and not just reciting that you looked it up on the internet and then know the answer to it, basically. Anyhow, let's get started. So the problem is you have an array of integers that are partially sorted. For example, 4, 5, 6, 1, 2, 3. And all of the integers are in increasing order starting at index number x. So, example case, I just told you, we have 4, 5, 6, 1, 2, 3. Now, the index that they start ascending is right here. And the problem is you need to write a method that returns the index that they start at. So in this case, that would be 0, 1, 2. You want to return index 3. Okay, so the method we are going to write start very simply is going to return an integer, and we're going to call it getStartIndex. And this is going to take in an array of integers. We'll call it numbers. Okay. And in here we have our implementation. Okay, so the first thing you want to do with your interviewer is talk through the problem. Try not to make any assumptions. Try to flesh out everything that's expected from the problem, get all your edge cases taken care of, etc. So, to make sure you're clear to start, walk through the example they gave you, make sure you know why the answer should be 3, and make sure that the answer is 3 and that you understand that. Go through a different example with them. So, let's say less obvious case, if it's, I'll add a second example up here. Let's say we have 7, 9, 1. Shorter array. Okay, so this still matches because it starts ascending at 1, this last index, wraps around, continues ascending, even though it's just a single element in the last position. So in this case, the answer you're looking for is index number 2, 0, 1, 2. So once you've talked through your problem, be it this one or another one, and fleshed out all of your assumptions, then you want to come up with test cases, then decide what algorithm you're going to use, and lastly get to the coding. Don't try to just jump into coding the problem. It's a common mistake. So, let's go over some questions you should ask specifically for problems that are based around arrays of numbers. There are a lot of them, and there are a lot of common questions you can ask that will help you determine what you need to do and what to be wary of in the problem, potential, not tricks, but things you can observe that will make the problem much easier to solve. So, first things you can observe about this one is, since you're looking for the position at which they start ascending, you look at both of these arrays, you notice that's going to be the lowest number in the array by definition, because that's where the start of an ascending sequence is going to be the lowest number. So really, if you want to frame this problem as find the lowest number in the array. A lot easier to think about, a lot easier to visually visualize, I guess. Okay. Some other important questions to ask your interviewer I'm going to go through real quick. Are duplicate numbers allowed? So, much harder here if you have 4, 5, 6, 1, 1, 1. You know, depending on what algorithm you use, that could make finding the lowest index very tricky. You could get a lot of the correct number, wrong index. So, we're going to say no duplicate numbers allowed. Are empty arrays allowed? Also no. Although they could very reasonably say yes, empty arrays are allowed, and then you would need to account for that. So, jot down some notes. I'm going to say no duplicate numbers. And these are questions you should be asking for all integer-based array problems, because you want to know the answer to all of them, and the answers to these questions can affect how you go about implementing your solution. No duplicate numbers, no empty arrays. Can the array be null? Easy to check. We're going to say no, but you still want to ask the question so that you communicate to your interviewer that you know to check for null. A lot of null checks in production software. That's a important thing to show that you know. No null arrays. Is 0 allowed? Or negative numbers? So in both of the examples I have up here, we have all positive integers. For sake of an interview question, we're going to keep it that way. Most interviewers will probably say no negatives, no zeros. If they do, then that's something you're going to need to consider. Generally, I think it's less common. No negatives, no 0. Okay, I think that's a pretty good set of questions about our inputs up here. So the next step we're going to get into is creating some test cases for all of these. I highly recommend coming up with all of your test cases before you start thinking about how you're going to solve the problem, so that you don't get biased by your own implementation. Which, once you have code in front of you that you've written and you really understand how it works, it's easy to ignore the spots you haven't been thinking about, which is why I recommend doing all of your test cases up front. So, what makes a good test case? These are both fine, but really you want to come up with one test case for each unique problem, I suppose, within the problem. So for example, easy way to start. Come up with a test case if there's only one number in the array, right? 5. This is a valid array. It's an interesting test case because there's only one number and your logic's going to need to handle this. In this case, obviously the lowest number in the array is going to be at index 0. Another interesting test case, only 2 numbers. So I'll add that over here. Say you have 3, 1. In this case, your answer is going to be index 1. Likewise, I think it's good to flip this around, have these in order. So, in general, some really common edge cases for arrays of integers and the associated problems. 1 element in the array, 2 elements in the array, an even number, which 2 handles, but also I recommend another case with an even number. So for example, 4 numbers. An odd number, so for example, 3 or 5. And then a large number of elements in the array. And then 0 elements and null are good things to keep in mind, but we've decided that they are not going to be part of this problem. So, having said that, we've got our 1, we've got some 2's, and since we're looking specific to this problem for an index of the array based on what order they're in, it's good to have both of these. Let's add a array with 3 numbers in it. We can use this one from up here. 791. The answer for this we want is 2. And let's add an array with an even number. We'll do 4 elements. We'll say, also specific to this problem, I should mention, we want to have a good mix of positions of the arrays with the answer in them. We don't want to have all of them be the first element. We don't want to have all of them be the last element, so we're scattering them around. So we'll make 2, well, let's not start with 2. Go 6, 8, 2, 4. Our answer is right in the middle there at index 2. And we'll go with a large number of elements in the array. Let's stick it way in there. 6, 7, 8, 9, 11, 1, 3. Alright, our answer in this case is going to be 0, 1, 2, 3, 4, 5. I didn't leave space for that. 5. Okay. Well, we've got this out of the way. We have these test cases to run through once the code is written that will keep you honest to make sure you didn't miss anything, so to speak. Next step. What algorithm are you going to use to try to solve this problem? Lots of candidates will skip the first 2 steps and jump straight to this to try to get into the coding as quickly as possible. All of the stuff we've just gone over is really important for communication and setting expectations, making sure that you are on the same page with the problem as your interviewer, which are parts of the interview process that are less focused on, but are just as important, if not more important, in the eyes of the interviewer. So, highly recommend not skipping these first 2 steps of talking through the problem, creating your test cases, and generally just making sure you know exactly what you're doing before you start trying to do it. Okay, so algorithm-wise, start out really simple, just show that you can solve the problem. If you're familiar with big O notation, start with something you know is probably not going to be the optimal solution, but is something that if you can't figure out what the optimal solution is, you can code just to show that you have your knowledge, that you have the knowledge and can implement it. So, working through this example, we want to find the lowest element in the array. Obvious solution, you go through the entire array and you keep track of which number is the lowest, and then which index it's at, you return that, right? Pretty straightforward. If you just do a traversal, it's going to be O of n time, which is fine, not great. It's not O of n squared. Hopefully that wasn't your first thought to jump to, comparing each number against itself. From there, you can see, hopefully pretty easily, as you go through here, once you find the lowest number, you know nothing else after that is going to be lower because they are in partially sorted ascending order. So you can stop there, which is better. Really, after digging into that, you can see that the condition you're looking for is irrelevant for all of the numbers as long as they're ascending. The condition you want is when one element right after the other one is less than the previous one. So in this case, the 1 is less than the 6. Only time in the array you're going to see that, and you know that the element on the right there is your answer. Now, that being said, there are cases where that's not going to come into play. For example, in our test case here, we've got the 1, 3. There are only 2 numbers. The one on the left is the answer you want to return, so you can't look for that specifically. Now, generally, if you see an array of integers and you're searching it in some capacity, like we are here, the algorithm you want to think to use that's probably going to be optimal or close enough to it for the interview is going to be a binary search. Think back to school. So, our binary search here in the array is going to be O of log n, which is shy of O of 1, which is not going to happen in a search. That's going to be your best case scenario. So that's a comfortable bet for the best algorithm, and one you should try to implement if you're comfortable with it, which hopefully you are. That will get you the farthest in your interview if you know the optimal solution and can implement it and communicate how you're going to implement it and think through the problem. If you do all these things, you're sitting pretty. So we want to do a binary search, which is going to be recursive. You can implement it iteratively, but it's going to be a lot easier, a lot cleaner in recursive form, and in an interview setting, you want to go for simple, readable, functional, more so than having really elegant code, I should say. It should be clean, it should be readable, but you don't need to go overboard dressing it up, so to speak. So, what do we need to do for a binary search in this situation? So we look at our example. Binary search, we want to get rid of half the numbers each pass. So we'd want to find an element in the middle, look at the left, look at the right, determine which half it is, go from there. Then go into that half, rinse and repeat until we have our element. So we're going to go ahead and make a helper method here because we're going to want a recursive method, and we're going to need the array, obviously. We're going to need a start index and an end index to look within. I don't see any other parameters we're definitely going to need. You can go from there and adjust. So let's call this binary search. Not feeling very creative. We have int binary search. And we need our array of numbers. We need our starting index. And we need our ending index. Can't see that. Just added a little closing bracket down there. Alright. So, before we get into implementing anything, let's pick our first test case, solve for that. We have a 5. Go ahead and erase this implementation and do our initial call. Get start index, return, binary search, pass in our array. Our start index is going to be 0, and our end index is going to be the length of numbers minus 1. So numbers dot length minus 1. Okay, so in the case of 5, we have our array, start index is 0, numbers.length is 1, minus 1 is 0. So, already got an interesting case here. Start is 0, end is 0. Because we're trying to make this recursive, we're going to need a terminating condition, which is going to go at the top of your implementation. Seems like a pretty good terminating condition, since at this point we can not assume, but we can set an expectation that at the end of our recursion we're going to have one element in the array, and we're going to want to return that. So we can say if index start equals end, then we want to return start. You can also return end, it doesn't matter, they're the same thing. And we are returning the index, not the number itself, which is an important thing to remember. Okay, so for our test case of 5, I already got a working solution. Our numbers include 5. We start at index 0, we end at index 0, we return 0. That's the index we want. It has the beginning of our ascending sequence. Good on this test case. Now, moving on. 3, 1. Okay. Now we have 3, 1, start is 0, end is 1, because the length of the array is 2. Doesn't meet this condition, got to do something else. Now's when we want to get into our comparisons and dividing the array into half and going from there. So we can say if now we're also going to need a middle index at this point in order to divide the array into half and compare. So I'll go ahead and create this, call it int middle. And because our array is only integers, we're going to want to use integer division to calculate this, which in the case of an even number of elements in the array is going to give us a rounding error. Or I suppose, yeah. It's going to be start, or not a rounding error, sorry. You'll see. I'm getting ahead of myself. Start plus end divided by 2, right? In the middle of the 2. Start is 0, end is 1. Integer division by 2 is going to be 0, so it rounds down. So now we have an interesting case where start and middle are the same thing, which is going to be interesting for our comparisons, and which is why I included this test case in the first place. So now we want to move into the left half of the array. If the first index, and the condition we're looking for here, first index is less than the middle index, we'll say it's 6 in this case, then we know our answer is not in that half of the array. Whereas on the right side, if our start index, which in this case is the middle index, is less than our end index, or the value at the index. So if 6 is less than 3, which is not, then we know it's not in that half. So since 6 is greater than 3, we know it is in this half. So I'm just going to add a condition to represent that. If our start index is, we'll say greater. If our start index is greater than not middle, not end, middle. Okay, so in this case, it's going to be in the left half. If our start is greater than our middle, then we want to call binary search again. With our start index because we're looking in the left half, start stays the same, and our new end index is going to be middle. Okay, so there's our left half of the array. Since there are only two halves of the array, we probably don't need to create another condition, and we can just say it's not in the left half, we know it's in the right half. We're going to return our binary search for the right half, which is going to be starting at the middle, ending at the end. Alright, very simple method so far. Let's work through some more test cases to see if it works. Let's go for our 3-1. That's the next one we've got queued up. Start index is 0, end index is 1. Let me jot these down. 0, 1. Start does not equal to end, so we're going to move past that. Middle, our middle is going to be 0. Okay, if the number at the start, which is 0, in this case 3, 3 is greater than number in the middle, also 3 because our middle index is 0. Okay, we can skip that. Now, return binary search with same array of numbers, our middle, which is 0, and our end, which is 1. Got a problem. In this case, we just tested, we get into an infinite loop using this logic because of integer division. So, how can we get around this problem? We can do a direct comparison of the two, add that as a terminating case. That would be easy, that would be straightforward. Seems like a good solution. Maybe not the most elegant, but like I said earlier, easy to communicate, shows that you recognize there's a case you need to handle, and should work for both of these. Just when you get down to two elements, you compare them. Let's implement that, and once you get past two numbers, then I think this will work. We can test through it and see. Before implementing that though, let's look through some other test cases and see what we can do there, and if there's any other things we need to consider before changing things. So in the case of 1-3, we have the same thing except another problem. Sorry, I'll explain. We get down to here, just like 3-1. If our number at the start, which is 1, is greater than our number at the middle, which is also 1. In this case, we don't want to go to the right at all. In this case, we want to go to the left. And can recognize here that we're comparing middle against end for our right, instead of middle against start because of integer division. So it makes more sense to compare the right side first, so that in this case we would have an actual comparison here instead of the same index against each other. So let's change that. We want to go right to left instead of left to right. Not obvious, but it makes sense because of the integer division. Sort of visually, oh, it's a good way to visualize this. You have, your comparison is more centric around the left element if you start at the left, whereas you start at the right, you kind of move quicker. That's probably not a good explanation, but yeah. So we're going to start with the right first. Hopefully working through the example will show what I mean better than I could explain in words. So if the middle is greater than the end, Okay, back to the 1, 3 example. Indices remain the same. If our number in the middle, which is now 0, 1, is greater than our number at the end, which is 3, then we want to search the left. Number in the middle is greater than the number in the... Okay, yeah. The middle slash start in this case, which is 1, is greater than 3. False. We do not want to search the right. That's what we want, because our answer is on the left. Now in this case, we go with a start in the middle, which is 0, and we do hit this case up here, the terminating case. So we fixed that problem because we adjusted for the integer division starting right to left. We have our 1 greater than 3, false, return binary search with start and middle, which are both 0. And so now we've only passed in the 1. Start equals end, return start, which is index 0. This is 0 in this case too. And we have our 1, which is the correct answer. So we have that test case taken care of. This one we still need to come back to. We're thinking right now we just have a direct comparison. Probably another way, including logic down here. We might stumble across it in these other examples. If not, I think that's a pretty good way to handle that case. Next test case we're going to go through is 791. Up here, 791, we have starting at index 0, ending at index 2, so we're searching the entire array to start. Start is not equal to end. In this case, we get a nice even middle number. 0 plus 2 is 2, divided by 2. We actually have a distinct middle number this time. So hopefully our comparisons will work as we want them to, and we'll actually go into a different half of the array. If our number in the middle, which is 9, is greater than our number at the end, which is 1, it's true. Search the right half of the array. Okay, so far so good. Numbers, our middle index is now 1, and our end is now 2. So we're now searching between 9 and 1, which is what we want. We go into the loop again, or not the loop, the recursion again. Starting in index 1, ending at 2. 1 plus 2 is 3, divided by 2. Integer division is 1. If a number in the middle, which is the same as last time. So, in this example, now that we've gone through the 7, we have the same problem as the one we ran into before. With this one, we have the higher number on the left, the lower number on the right. We need to return the number on the right. And we have the middle, which is 9, greater than the number on the end, which is 1, and we get into another infinite loop. Another one where we should probably add a second terminating condition that compares the two if there are only 2. Okay, we'll go to a next example. One more example just to make sure, then we'll implement that, and then we'll go through the long example and make sure that works. Next example, we have 6, 8, 2, 4. Start index will be 0. End index will be 3. Middle index in this case is 0 plus 3 divided by 2 is 1. So our middle index is right here, it's just 8. So we are not directly examining the 2 here, which is interesting, because that's the number we want to return. Our number in the middle, which is 8, is greater than our number at the end, which is 4, which is true. We go into the right half. Now the 6 is gone. Pass in the 1 and the 3. So far so good. We don't want the 6. Now we have start and end. Makes our middle 2. If our number at the 2 spot, which is 2, is greater than our number at the end spot, which is 4. false. We do search in the left, so we have our start of 1, our middle of 2. Now we're just looking at the 8 and the 2, which you can already see is the same problem we're going to have here. Let's go through it just to make sure. 1 plus 2, 3 divided by 2 is 1. Our number at the 1 spot, which is 8, is greater than our number at the end, which is 2, which is false. Then we go and do another search of the left half. Or wait, hold on, I did that wrong. Our number in the middle, which is, our number in the middle, which is 8, is greater than the number at the end, which is 2. This is true, so we go into the right half again, which has the same 2 parameters. So we have the same infinite loop. Don't want that. Don't want that at all. So, this is going to be sloppy. Close this off. We're going to insert this other condition right up here. If we have 2 numbers in the array, then compare them, return the lower one. Or really, because we know if we get to this spot, well, let's just handle both scenarios. This one worked out, but I think it would be more work to avoid this than it would be to just handle both of them. So, we'll insert in here if, let's see, if they are 1 apart, so if end minus start equals 1. Make sure that adds up. They should always be 1 apart regardless of where in the array you are. Okay, looks good. N minus start equals 1. Then we want to return and then just compare the 2 numbers. So we'll say I'm going to use a shorthand version of this rather than write out a bunch of if statements. I can explain what it means afterwards just in case it's uncommon. If our numbers at start is less than numbers end, then we want to return. Okay, so if our start is less than the number at the end, then we want to return start. And if it's false, we want to return end. Okay, so shorthand, what this means. This is question mark and then the colon. What this means is if this condition here is true, then return this value. If it's false, return this value. Oh, can you see this? Yeah, okay, perfect. Okay, so let's work through this again one more time. You can just use this example because we know the rest of them are the same. Start index is 0. Our end index is 1. Our middle index is 0. Well, we don't get to middle yet. So start equals end. Does not. We continue. Go down to this block. If 1 minus 0 equals 1, which it does, okay, we return, okay, if number at start, which is 3, is less than the number at end, which is 1, which is false, we return end, which is 1, which is the index of the number we want. So this works, and now we know these two work because they get into this similar state. Now we can do the big one. Make sure, safety check, all of our logic holds up at scale. Well, scale for, 8 numbers. But if this works out, then I would be confident that this code will work at scale for however many numbers we throw at it, because it will eventually get into one of these states because of the recursion. So we have 1, 2, 3, 4, 5, 6, 7, 8. Length minus 1. We have end is 7. Start is not equal to end. End minus start is not equal to 1. Now we can go into middle. 7 divided by 2, because of integer division, will be 3. If our number at the 3 spot, which is going to be this 9, is greater than our number at the end, which is this 5. So this is true. We go into the right half. Our new start index is going to be the 3, and our end is going to stay the 7. Our new middle is going to be 3 plus 7 divided by 2. Our new middle is 5. If the number at the 5 spot, which is this 1, the 1 is greater than the 5, this is false, skip this. Now we return our new start is 3, and the middle is 5. Okay, so far so good. 3 plus 5 is going to be 8. Our middle is 4. The number at the 4 spot, which is this 3, is greater than the number at the end, which is this 5. False. Go into the left half again. Our new start is 3. Our new end is the current middle, which is 4. It's looking good. We're down into our final terminating case. Start equals end, which is false. End minus start equals 1, which is true. 4 minus 3 is 1. We return number at start, which is 3. It's going to be the 9. Or wait, sorry. Yeah, this should be 4 and 5. Pass this in wrong. Let me go through that again. I said the wrong thing at some point. Okay, so we did 9, 5, went into the right half again. So our start is 3, and then our middle was the 1, which is the 5. Okay, let's start here. Middle is going to be the 4 again. Oh, I see what I did. I compared... Yeah. There's our 3, there's our 5. Sorry. Okay, so if our number in the middle of the two, which is 11, 11's at the 4 spot, is greater than our number at the end, which is 1, which is true, then we go into the right half. And our middle is 4, our end is 5. That's where I made the mistake. It's important to go through all of your examples because everybody makes mistakes. It's easy to overlook something or kind of get sidetracked in thought with what you think should happen versus what the code actually says will happen. Very important to go through your examples. So now we have 4 and 5. Now we're down here. For a number at the start, which is the 4 spot, 11 is less than the number at the end spot, which is 1. 11 is less than 1. False. So we're going to return our end, which is the 5, which is what we want.